So, welcome everyone. Today we have a presentation from Raheb, and we will be recording this session. But everyone participating will not be shown in the recording unless you ask questions afterwards. And we will open up for questions after the presentation is finished. So then I give the word to you, Raheb.
Thank you a lot. Thank you, Shashti. So I will directly go to the topics, and first I have to say hello, and then I directly go to the topics. So first I have to say that I cannot see the participants, so I'm just seeing the screen. So thank you for attending the presentation. The topic about the safe and ice-free roads and bridge using the renewable thermal energy sources. Here I specify about the using hydronic heating pavement. For this special presentation, I'm just focusing on the roads and not bridge, but the model that we developed is possible to use for bridge and every different section for the roads. Very shortly, I would say that who I am. I am Raheb Mirzanamadi. I did my bachelor in civil engineering in Tehran Polytechnic, and also I did my master in transportation and road engineering in Ferjefri University in Iran, Tehran. And at the moment, I am doing my PhD in building physics at Chalmers University of Technology, Sweden. At the moment, I am in my 4th year of PhD, 3.5 years already passed. So probably I can give some good results from what I did so far. I already did in last March, or March 2017, my licentiate, and now I am going forward to doing the rest of my works to get my PhD. In the right side bottom, you are seeing Statens vegvesen's icon, which is supported financially the project, and also the Chalmers University of Technology, which is also partly supported the project financially as well. So I have to say thanks for both of them. The picture you are seeing in this screen is almost explaining what I am going to talk and what is my project is about. The road is almost is icy here, and it's very important to say that the icy condition, sometimes called the black ice as well, when there is a very small layer of the ice on the road surface, which the driver is not aware of it. But and the reason was that the color of the ice, since the layer is very thin, the color of the ice is almost the same as the color of the road. This is very dangerous when the drivers are in special sections like slopes or curves, which need to change the friction of the vehicle. So the goal of the project is to melt the ice or keep the road ice-free for this special section like slopes and curves. So there are 5 people at Chalmers which involving in the project. Kyle-Erik Agentoft, Bijan Zarabi, Harry Johansson, Yusuf Jansson, and me. This is Hamlet from Statens vegvesen, as you can see. So me and Yusuf working at the same time in this project very closely and tie to each other. Almost Yusuf before licentiate mostly focused on the storage parts, and I mostly focused on road section, the road parts of the hydronic heating pavements. So I have to say that the research I did here in the last 3.5 years resulted in a few publications, which the presentation is based on these publications. The first one, the 2 journal published papers. one in construction and building technology, building materials, and another in Journal of Cold Region Science and Technology. And the one accepted conference paper in cold climate, which will be held in March in 2018 in Kiruna. I will give the results from these papers in detail in this presentation, and also there's two ongoing papers, which one is related to the hybrid 3D numerical simulation model, and another application of model-based prediction control method, which I will give an introduction or the brief results of this research as well for this presentation, for this studies as well. So we start. Last week, my colleague Yusuf Jansson presented his studies, his work about the ice-free roads and bridge. So and he gave a lot of information about what's the problem related to the current methods for removing the ice and snow from the road surface. I'm just giving a very brief introduction about the problem, and then I will go forward to see what we are doing and what's the alternative methods. So at the moment, the most common method to remove the ice and snow from the road surface is distributing salt and sand. However, the problem is not very environmentally friendly. Yeah, as you can see from this slides, the usage of salt and sand is very high. It's caused damage to surrounding vegetation. Its effect on the soil, it's damaged both surface waters and the groundwaters, and also it makes corrosion in both infrastructures and also vehicles. Another problem for the sand is that when they are distributing in slopes, the agents can move to the bottom part of the slope. Then the concentration in upper part will be low, and then it's really hard to remove the snow, this low concentration. Another point was that it's not recommended to distribute sand and salt when the temperature is -8 degrees. So this means that it's not always easy to use the salt and sand. Another big problem is that if you distribute the winter maintenance authorities distribute salt and sand after the slippery condition occurs on the road surface, it means that first the accident will occur, then they remove the slippery condition. This is very dangerous. So what will be the alternative, especially for that critical section like slopes and curves that the drivers change the friction frequently? It will be a good idea to use hydronic heating pavement. Hydronic heating pavement consists of embedded pipes in the road, which effluate as thermal carrier energy circulates around the road. During the summer, the road surface gets almost warm, and then it's possible to save this energy in seasonal thermal energy storage. During the winter, it's possible to give back this energy to the road, to the pipes, to melt ice and snow from the road surface. It's very important to say that in this project, we are only focused on the removing ice from the road surface, anti-icing. We don't care of the snow, because we assume that all the snow coming down to the road surface is already flowed away from the road surface. So it's very important. I will give this in details in the coming slide, but it will be important to keep in your mind. Main part of the heat, as you can see here, is transferred inside the road. Most of the road section in both in Scandinavian countries, I mean that in Sweden and Norway, are consist of asphalt. So it will be very important to see that what's the thermal conductivity of asphalt material. Another thing was that it's very interesting to see how different design options related to the hydronic system, such as the distance between pipes, the size of the pipes, can affect on the efficiency of hydronic system for anti-icing the road surface. So, as you can see here, the goal of this research is to first find out the thermal property related to the asphalt material. Then, before licentiate, we focused on finding a 2D method for understanding the operation of hydronic heating system for anti-icing the road surface. It is very important to understand the 2D system because the boundary condition on the road surface is almost super important for this kind of system. The second step, which done after licentiate, the third step, which done after licentiate, was to develop this 2D model to the 3D model. And after that, we tried to find out what is the optimal amount of energy to find to anti-icing the road surface using the 3D model. So if I show my research outline, it will look like this. The thermal property of asphalt concrete, which is determined both experimentally and also numerically. The data is implemented into the numerical models related to the hydronic system, and two types of the numerical model is developed, a 2D model and a 3D model, and the rest, an application of model-based predictive control model, is developed to find out the optimal and the minimum amounts of heat to anti-ice the road surface. So I'm going to details and talk about that how we measured the thermal property. First, I have to say that there are different methods generally to measure the experimental measurements for the experimental measurements of the thermal property. The main method is steady state. But there are two problems for the steady state. First is the time. It almost takes 2 days or 1 day. And the second was the size of the sample. For example, at Chalmers, we have a guided heat meter, which guided heat flow meter, which requires 30 centimeter to 30 centimeter samples. Since we have a lot of samples to measure, then we prefer to use a faster method, which is related to transient plane source TPS method. TPS, as you can see from the picture from the left side, is used as sensor design. The sensor design here work as heat source, and at the same time it work as thermometer and get the temperature at the surface of the sample. This sensor size is located between two identical samples, and the temperature variation at the surface of the sample is used to get the thermal conductivity and the thermal diffusivity and the volumetric capacity of the asphalt samples. From the experimental samples, from the experimental method, using the experimental method, we were able to get 5 different sample types or asphalt types, which most commonly used in Sweden to construct the roads. As you can see, the thermal conductivity of asphalt, for example, for ABT11 is 1.39 watt per meter per Kelvin, and for ABS16, is 2.24. We found out that for minimum amount of the asphalt concrete, thermal conductivity is almost 1, and the maximum is almost 2.5. Just other random calculation, but this is the purpose, the aim, the calculation, which the details are presented here. So the next step, which we did, were made a numerical model of the asphalt concrete. As you can see, a sample around 45 millimeter in 45 millimeter is built. And in the numerical simulation, as you can see from the right slide, right picture, the aggregate shape is cylindrical. And the reason was that from literature we found out that when the aggregate distributed randomly, the shape does not affect on the measure and calculating thermal conductivity. So here the gray circles are aggregate, the blue circles are air voids, and the white area are binder. The distribution of aggregates are made in MATLAB, and then they implemented to the console to get the thermal conductivity using steady-state method. I will show for each type of that 5 type asphalt types, 3 different numerical models, simulation models of asphalt concrete is built, and this for each of these 3 different numerical models, the thermal conductivity I calculated in 2 different sites by putting adiabatic boundaries and the temperature difference in the boundary for each sample, and then the mean heat conduction is used to calculate the effective thermal conductivity for each sample. The result I presented here show a very promising numerical model. As you can see, the relative difference between experimental results and numerical results are very close to each other, or at least for some special samples are very close to each other, and the maximum difference is 8% and the minimum is 1.5. So in generally, you can say that 1% to 10% relative difference we can have for this numerical simulation model, which is show that we can use this numerical model to investigate different design parameters of the asphalt concrete for calculating the thermal conductivity. The advantage of numerical model was that it's much faster comparing to experimental and can give a good result, good hints about what will be the experimental measurement. 5 different parameters, including air void content, aggregate types and gradation, modified binders, moisture effect, and the maximum effect of saturation and freezing is investigated using the numerical model. And just to close off this section, I'm giving some results and conclusion from what we get from the investigation. We found out that increase in air void content led to a decrease in thermal conductivity, and also changing the aggregate types from diabetes, which is lower thermal conductivity related to have with quartzite with higher thermal conductivity related to have almost 50% increase in thermal conductivity. The details of this study already presented in the publication, which I already showed. So the second track of this study is related to the hydronic pavement. In this part, I'm talking about three different research which we did: 2D model, 3D model, and a predictive control model. But before I'm going to say that again, that in this study we assume there is no snow on the road surface, and the slippery condition only occurs due to condensation on the road surface. 7 different heat flux, including long wave radiation, short wave radiation, or solar radiation, precipitation including rain and snow, sensible heat related to the precipitation, not latent heat, which is related to the melting ice, because all melting snow, because all snow is already flowed away. Evaporation and condensation, which is the reason of this slippery condition, and also convection and conduction I considered for this study. The ambient temperature is implemented to the 2D model, as you can see from the left picture, in order to measure the how much heat we required to melt the road surface, the ice from the road surface. The data for this study are obtained from Sweden, motorway E18, for validate the results, the numerical model, and also Ostorsund. The Ostorsund, my colleague Yusuf already explained the detail about why we selected Ostorsund. The reason was that there is an ongoing project at the moment in Ostorsund for a field study related to the hydronic pavement. So the reason, that is the reason why we select Ostorsund climate data. Another reason was that Ostorsund is a cold area with a long period for winter, which is very interesting to simulate the anti-icing operation for hydronic system. So the model, numerical model, generally developed to obtain the remaining number of hours related to the slippery condition at the road surface, and also the required energy annually for needs for remove the ice from the road surface. We put some regulation to start and turning on the system. Here we assume that whenever the surface temperature is lower than dew point temperature and the freezing temperature, the slippery condition will occur on the road surface. 2, get rid of the condition that first slippery roads occur, and then we melt the ice. To enhance the model or to keep the road ice-free for forever during a year, we add a threshold, as you can see, delta T, to the models. It means that this threshold leads to have no ice on the road surface, and all slippery condition will be removed using the hydronic system. All of these thresholds have to be upper than 0 degree. I will show the result related to this threshold and this to the numerical model. As you can see here, the result is presented. The surface, the equations are presented in the upper part. The figure in the left is related to the annual required energy, and the left figure is related to the number of the hours which is slippery condition occurs on the road surface. If we focus on the figure in the right side, you will see that by considering only a very small temperature for the thresholds related to the dew point temperature, 0.1 degree, the slippery condition tremendously reduced. However, keep this in mind and look at to the left picture. You will see that the amount of energy didn't change so much. It's almost close to 8 kilowatt hour per meter during a year. So it means that the slippery condition or the hydronic system is very sensitive to the dew point temperature. Just again look at please to the right picture, you will see that the bars that are tied to each other, they are related to the freezing, the threshold of freezing. So the sensitivity of these numbers are not very high for freezing temperature. So it shows this is very important result. Means that to keep to run the hydronic system, it's very important to have a threshold temperature for the dew point. And this is a very simple method to run the hydronic system, which already I will use in future. I will show another study which we did a complicated method to obtain the optimal heat. But this is a simple way and a different way as well. To remove almost the sweater condition from the road surface and have a very little increase in the energy. So I'm going forward. There is a question always raised related to the 2D model. 2D model is a section in which a constant temperature is set to the pipes. But there was no decline in the pipes when it's the fluid circulates it. This question arises and then led to develop a 3D model, which is possible to have the inlet temperature and then get the decline temperature along the pipe and have T out, means that the outlet temperature. For the 3D model, as you can see from the figure in the left, the road section and hydronic heating pavement are divided into smaller sections, and as you can see from the right figures, these smaller sections, this vertical cross sections are connected serially to each other to make a 3D model section, a model for the hydronic system. It's important to say that the model is adopted from the Carlson Henrik, which already did his PhD at Chalmers. The model in our division is developed both by me and Youssef. Youssef did in Python and I did in COMSOL to see the difference. It should be said that this model is almost dependent on the 2D section, as you can see from the right figure. We already before my licentiate, we already did a lot of research on the 2D models and validate the model both by experimental results and also using the analytical results. So we were almost sure about the 2D model, and then it was possible to connect them serially to obtain the 3D model. This is the reason why we select this method. Also, the 3D model is validated by itself with a numerical simulation, with analytical solution, which determine the drop of the temperature along the pipes. The equation which used in analytical solution is presented in this picture. T out is equal to the Ts, which is the surface temperature. Here it's assumed to be 0 degree. T inlet, which assumed to be 10 degree, and T minus Ts, and the exponential of the length of the pipe, which is assumed here to be 160 meter, and small l, which is related to the characteristic length, which is related to the resistance between pipe and the surface, the speed of the fluid, the inner diameter of the pipe, inner radius of the pipe, density of fluid, and all specific capacity of fluid. The section of the road tried to be simple, only one layer, as you can see from the left picture, and the results are presented in the right. As you can see, the results are very close to each other. The maximum difference is less than 4%. It should important say that here only 4 cross-section is used. If I used more cross-section, which I used in my research as well, but not presented here, for example, 11 cross-section, then the results will be almost super close to each other, and the difference will be less than 0.45% relative error. So I'm going forward. This 3D numerical simulation model is used to obtain the distance between pipes, embedded depth, pipe diameter, fluid temperature, and the fluid flow rate. I'm giving a result related to the pipe diameter. As you can see here, when outer diameter of pipe varying from 30 millimeter to 13 millimeter to 30 millimeter, the number of the hour of the slippery condition reduced. This is almost even makes sense, because by increasing the size of the pipe, then the amount of heat reached to the surface will increase. But the interesting point was that after 30 millimeter, the system works worse in an opposite trend. And the reason is related to that the fluid regime changed from turbulent to laminar. As you can see from from the right figure, the thermal resistance between fluid and the pipe valve suddenly increased when the outer diameter is higher than 30 millimeter, and this is related to the fluid regime. For ultrasound case, we found that the annual required energy for anti-icing is about 91 kilowatt hour per square meter during a year. This 3D model, for 2D model, it was 81 kilowatt hour per square meter, which shows that 3D model is almost 10 watt higher, which is reasonable as well, because here we have the temperature drop. And the risk for slippery condition is almost reduced down from 2009 hours to 137. Comparing to 2D model, it's almost 10 hours more slippery condition at the road surface. And an obvious result that by decreasing the distance between pipes, the performance and efficiency of the hydronic system will increase. Placing the pipe closer to the road surface, increasing the outer diameter of a pipe. But as I mentioned, the previous section should be careful that the fluid still be in the turbulent regime. And increasing fluid flow rate result in improving the efficiency of the hydronic system. All details are going to be presented in a paper. We hope that probably in 1 or 2 months we are going to submit it in detail. So the last part of the study which I did so far related to the hydronic pavement was that what is the minimum amount of energy or optimum amount of energy which is possible to use keeping the road surface ice-free. So to obtain this result, or to approach the question, we divided the hydronic system into 2 parts. As you can see from the left picture, the left picture is presented as the whole system. The middle system is presented the system when there is no turbulence in the system. I mean that the surface temperature is 0. And the bottom temperature is 0, the initial temperature is 0 as well. And the right picture is related to a normal hydronic system, which there is no heat inside the pipes. So it's presented almost a regular road without any pipes. The middle section is used to obtain the elementary response of the heat in a control point when the heat is injected to the pipes. This is very important. The control point, I have to say, that is a point, the road surface between two pipes in the last point of the in the last section, means that they're exactly on the outlet section of the road. And the left hydronic system, the left system, is used to obtain the temperature on a road surface when there is no heat. It means that from this section C, we can possible to obtain the temperature, the slippery condition, the temperature which on the road surface which leads to the slippery condition. It's very important to say that this dividing is possible when we consider a linear equation for the system. The summation depends on is based on the superposition. In the superposition, it's important to obtain a equivalent temperature and also a constant coefficient on the road surface. This equivalent temperature should be investigated. How will be differ from a case that all heat comes to the road surface? Means that in this model we try to make a simplification. This simplification should be compared with the total conditions. But first I am going to say that what is the simplification. Here we assume that the equivalent temperature at the road surface only obtained from convective heat flux, long wave radiation, and the short wave radiation or solar radiation. Means that only from the dry roads, and the wet part of the road, including the sensitive heats of the rain and the snow, and also condensation, evaporation, are ignored. The equivalent coefficient of the heat at the road surface depends on the convective heat coefficient and also the radiative heat coefficient, and equivalent temperature obtained, as you can see from the equation. The constant hydronic coefficient, constant coefficient of convective heat coefficient times to ambient temperature, and constant radiative heat coefficient times to the sky temperature plus the solar radiation, which we know that the observability is known for us, and also the irradiation related to the solar, the short wave radiation is known for us as well. So the result compared, the result obtained related to the surface temperature, which obtained from using the equivalent temperature and the total heat flux compared with each other. As you can see, the results are very close to each other. If you look at to the table at the bottom, the mean error difference between the surface temperature obtained from the equivalent temperature and the total heat flux are 0.35, and the mean absolute error is 0.4. It means that the simplification leads to a promising result for us. And furthermore, the equivalent slippery condition which obtained from the equivalent temperature and also the total temperature are very close to each other, almost 50 hours difference, but this means that we can use this simplification. And as you can see from the result, equivalent temperature led to bit more slippery condition, and the reason was that using this equivalent temperature at the road surface leads to colder surface. The difference means that the mean error is related to the, as you can see from the equation in middle, is related to the surface temperature obtained from the equivalent temperature minus to the surface temperature obtained from the equivalent temperature. So using this simplification, we can obtain the we can obtain the optimal hit. But first, we have to obtain the elementary response as well. We try to inject the 1 watt heat into the hydronic system, and then from there we find the temperature variation at control point. It should be said that here that 1 watt is not important. It can be 10 watt, doesn't matter. But as you can see from the right picture, the elementary response is the temperature divided to the wattage. So this curve always look like this because it's respect to the linearity. And after 2 weeks, we assume that the elementary response get constant. So heat pulses, consider it to be injected to the pipes. There is a special duration for each heat pulses. Here we assume that the TP is equal to 1 hour. It can be everything, but here it's in line with the climate data we have. It's important to say that heat pulse should be upper than 0 degree. Could not be lower than, because in that case the system will start to cool down the surface, which is not interesting. Then it always has to be upper than 0, which is injected and hit the surface. And I have to say that there have to be some upper boundary. Otherwise, we cannot inject it in tremendous or huge numbers. We have to be always in practice. In this study, it's considered to be 1,000 watts. So just very quick, almost 2 slides left, so I have to be quick here. Then considering and assembling what already I mentioned, you can see from the upper pictures, this together for only one heat pulse. The optimal temperature response can be obtained using the elementary response in the beginning of the heat pulse and the end part of the heat pulse, and then minus them from each other. It will result in the operative temperature response for each heat pulse. So assume that we have this operative temperature response in the right figure for all of the pulse during a year. Then, using this operative temperature pulse, it will be possible to obtain the optimal heat. The results presented here related to the Ostersund minimum required energy for anti-icing the road surface during a year is almost 110 kilowatt hours per square meter. If you compare this with what I obtained from 3D model, the 3D model was 91. It means that this heat is almost 20 kilowatt hour more. But using this heat means that there is no slippery condition on the road surface during a year. However, in the 3D model, using that 91 kilowatt hour, we have already 137 hours slippery condition. So this is the minimum. It's important to say that this is the minimum amount of the heat we can have. And the maximum inlet temperature is important. That is need to have 12 degrees. It's important. We cannot have 60 degree at price. And this is the reason, as you can see from the figure, the maximum and upper limit is the 1 watt. So just to summary, first the group is measured the thermal conductivity of asphalt. We made a 2D model, 3D model, and also obtained the optimal heat to keep the road surface ice free. Many thanks for you listening. I'm sorry that almost a bit more than 45 minutes, but I'm ready for questions.
Okay, and we can open for questions in writing if you like, or you can unmute and do them orally.
I don't know. I'm open for every situation that you like. Then just I cannot see the questions. So I will be happy if.
I will read them to you as they come up, but I could start with a question myself. I didn't get, you talked about the amount of heat that you needed and the energy and how many hours of slippery road. But do you need, to make this work on a road, do you need any extra infrastructure? And how can that be maintained?
You mean that, for example, extra infrastructure, you mean that putting pipes under the road, or you mean, for example, holes, or?
No, I mean about the energy demand that you have, and how will you solve that, and how will you maintain it in a very effective way?
This is a very good question. So it's absolutely the project almost consists of two parts. The first part is that how much energy which we need, which is almost my research question. And another part was that how we have to provide this energy. This energy provided by borehole and harvesting energy in borehole, which is a question, main research question, or part of the research question related to the user, and he answered almost the question before his licentiate. But about the maintaining and keeping this energy on the road, I would say that it's not easy to say, but the reason that we tried to remove the snow from the roads, if it's only focusing on ice-free, was to make it possible to that the amount of energy we can harvest it and save in storage is enough to melt the ice. But I don't know if I answered your question or you mean a different thing.
You answered part of it.
Probably I didn't understand your question very clearly.
But as you said, it's a big question, and the part about how we should maintain such a road, it's also a very big question afterwards.
Yeah.
So let's see. I don't see if we have any questions coming up. It was just me writing that questions could be posted. Okay. Yes.
Kjersti, I'm here. Even Nedrebø. I've been listening to this. I guess I haven't got all details, but I'm working with the Bjørnafjord floating bridge, and for the Bjørnafjord, we have a giant energy source. We could pump water into pipes in the asphalt layer. And in Western Norway, we have a long winter time where the temperature is around 0. So it's going from ice to rain, from ice to rain. And a good idea here would be to get rid of the chlorides on this steel structure to prevent it from any rust degradation, and have maintained, say, a safe temperature for the road surface. So I wonder if it could be the energy calculation for that, if we were thinking of only pumping seawater, which is like 5 degrees or something, how much water would be needed per square meter to keep if we do some kind of calculation, because this is also very interesting in summertime, because our bridge, which is 5,000 meter long, in a warm summer day it expands due to heating, and we could use the same system then to reduce the length elongation and simplify our structure, if it pays off, if the money questions in this is nice, and it doesn't take energy from if we don't need to add energy, we have enough energy in the water, and all it takes is to have energy for the water circulation. That could be an interesting evaluation to do, I think.
Yeah, if I want to answer your question, first, at the moment I cannot say exactly what amount of the water you need, but I can say that the model which we developed for both 2D and 3D is almost focused on a very low temperature, almost 5 or 6 degrees, and this is a very promising. So I can say that you can use this amount of a temperature to get rid of the ice on the road surface. This is very promising, but for the snow melting, this is a bit hard to say. Then there needs to be investigated. And also, since just part of your question I missed because the internet connection is almost disconnected. But I would say that if the road, the pipe section is really long, then the drop will be high as well. So generally, what we did in model is very easy to investigate your question. Very easy for part of it. But probably it will be the question that if you consider that long sections and using the amount of head, the drop will be high and probably will need to be investigated. But generally, it's possible, I would say.
Okay, thank you.
Thank you, Hela.
Yes. And I have a question here from Gaylord. Vehicle pavement interaction often generates some heat. Is that accounted? If yes or not, which effect can such a heat source have on total energy demand per square meter?
I didn't understand the first part of his question. What is produced energy?
The vehicle pavement interaction. Yeah, so the rolling resistance.
Yes.
Yeah.
This is a good question. First, thank you and hello to Gaylor. The question for this study, that part of traffic is almost ignored, and this is the reason was that we assume the road is slippery during night, and the first coming vehicle will be affected by the slippery conditions. So the traffic is almost ignored in this study. For the interaction between vehicle and the road, they are using a piezoelectric, which is out of the scope of this research. But I would say that this is an important question. We already had in our mind that the traffic can reduce the risk for the slippery condition. But in this study, we only considered for the first coming vehicle. So we did.
The comment back is perfect.
Thank you.
Okay, do we have any more questions from those joining online? I cannot see anyone asking questions or writing. Then I think we will say thank you, Raheb, for a very interesting presentation, and I think that you will have to talk more to our people at the Bjørnafjorden project.
Absolutely.
They will be interested in hearing your calculation on the energy demand for their bridge.
I am interested.
Yeah. Yes, we are interested, and I have my colleague Bjørn Tangvall. I guess he will contact you afterwards, and we can hear more from you and collaborate a bit. Thank you very much.
Thank you.
Okay, thank you. And then I will stop the recording, and we will have another presentation next week. Let's see, on the 15th, then we will have Sania Sun. She will be presenting the constructed stormwater management. So I will wish you all welcome back in 1 week. That will also be at 10 o'clock. Okay, thank you.
Thank you, Kjersti.